When a centralized database hits its absolute processing limit, the physical server overloads and the entire system stops. To prevent that single point of failure, enterprise architectures distribute the load, passing queries across a network of scattered nodes instantly. Moving from a single server to a network requires a specialized design process. The architect has a clear mandate: take a unified logical data model and translate it into scattered data fragments and software programs across multiple physical locations. You cannot simply copy a centralized database schema, paste it across a dozen separate machines, and expect it to function. A network introduces physical variables that do not exist inside a single machine. Geographic distance creates latency. Communication between nodes is asynchronous. System constraints move from internal bus speeds to the finite bandwidth of the network connection. Designing a distributed database management system requires a rigorous top-down architecture pipeline to manage those constraints. The overarching objective of this pipeline is to find an exact mathematical balance between processing locality, keeping data near the application that needs it, and workload distribution, spreading the compute demands across the network. This phase of the design process is entirely conceptual. It happens independently of whatever final hardware configuration or software suite a company chooses to install. The shift from centralized to distributed design requires a different kind of architectural thinking. You are ultimately trading the simplicity of a single server for the geometry and survival of a network. The top-down pipeline begins by designing the global schema. Exactly like a centralized database, the architect must first map the entire data universe to understand what information exists. Before breaking that global data apart, the system's operational requirements have to be profiled. Every site on the network is evaluated across 3 intersecting axes. This 3D matrix maps system usage patterns. The vertical axis, access type, determines if interaction is static reading or dynamic updating. The depth axis, level of sharing, defines what is distributed to a node. Finally, the horizontal axis, knowledge level, specifies if terminals need full or partial information. Alongside plotting these vectors, architects capture raw system metrics. They track application execution frequency, daily processing volume, and pinpoint the geographic origin. By combining the global schema with rigorous site profiling, the architect creates an empirical blueprint. This blueprint dictates exactly how to safely break the database apart in the next phase. Phase 2 operates on a strict rule. Distributed systems do not allocate whole databases. They distribute fragments. The monolithic global schema is systematically broken down into distinct mathematical slices. Horizontal fragmentation slices the rows of a table, grouping records by specific cities or regions. Vertical fragmentation slices the columns, grouping specific data attributes together, like separating financial transactions from contact info. This slicing provides a distinct architectural advantage. Fragmentation dramatically increases system concurrency. Instead of sending a massive, complex query to search a monolithic table, the network breaks that request down into smaller subqueries, targeting specific data fragments. Those subqueries are executed simultaneously across multiple nodes, each holding a different piece of the puzzle. By fragmenting the data, a single processing queue becomes a massively parallel execution engine. A single query can now access multiple local fragments simultaneously. This drastically reduces the time a transaction spends waiting for data locks.
Phase 3 is allocation. We now take those logical fragments and map them to physical geographic sites. Every physical allocation decision is governed by a strict optimization trilemma. The first goal is processing locality. We want to keep data physically close to the primary application that uses it. High locality maximizes local references and eliminates costly, high-latency remote network jumps. The second goal is workload distribution. The compute load must be spread evenly across the network. If we maximize locality too aggressively, we might dump all our data onto one busy site, creating a bottleneck that saturates the local server CPU. The third goal is data availability and reliability. The system must survive individual site failures. If a node goes offline, the network still needs access to that information, which inherently requires building data redundancy. Every allocation choice is a zero-sum compromise. Mathematically prioritizing one of these 3 goals inevitably degrades at least one of the others. To solve the trilemma, architects evaluate their network against 4 core distribution strategies. Strategy 1 is centralized allocation, where all data lives in a single geographic location. Centralization creates high communication costs for remote users and introduces a single point of failure. If that site goes down, the entire distributed network halts. Strategy 2 is partitioned allocation. Data exists in one place only. This yields high locality but low availability. If a node goes dark, its unique fragment is lost to the network. Strategy 3 is replicated allocation, which solves the availability problem by creating full or partial duplicates of the database across multiple nodes. Replication provides massive availability for applications that primarily read data. However, if data needs to be updated, replication introduces immense synchronization overhead to keep every copy perfectly matched. In modern systems, physical storage space is cheap. The true constraints come from CPU usage, disk I/O, and the network communication required to synchronize duplicates. Strategy 4 is hybrid allocation. This is a pragmatic approach. Architects replicate only the most critical, highly read data for availability, while strictly partitioning less critical data to save on network overhead. The chosen distribution strategy encodes the system's operational priorities directly into the architecture. It dictates exactly how the network will behave under stress. Once the allocation strategy is set, we move from the high-level geographic network topology down to the physical hardware of an individual site. This brings us to the final step of the top-down pipeline, designing the local physical database schema for each independent server.
These local databases are now configured. They house only their specifically allocated fragments or replicas, operating completely oblivious to the rest of the network outside their walls. We started with a monolithic global schema, sliced it into fragments, traversed the network, and landed inside a local database. The end user must experience the illusion of a unified, centralized database, completely shielded from the geographic complexity executing behind their query. There is no single nils and making calculated trade-offs. Architectural success depends on knowing exactly when to sacrifice network I/O capacity to guarantee system availability. Distributed database design is an engineering balancing act. The logical perfection of your data model must be built to survive the physical reality of the network.